Hello everyone and welcome to the second part of this lab, which has to do with polarization. In the first part we did with light. It wasn't polarization yet, but we dealt with the refractive index because we had a lens that refracted the light and helped us to create an image. Here we're going to have a phenomenon called as polarization, and that will help us find what we call the Bronstein angle. What essentially is the Bronstein angle? Technically, the Bronstein angle is the angle at which you have an equal amount of reflection and an equal amount of refraction for every given light signal. All right. So, in order to find the Bronstein angle in this experiment, in this lab session, I will show you what the lecture is like, and I will give you, when we conduct the experiment, I will give you the data that you need to use for the computation of the results. So our experiment will be simple. We'll have a light source, okay? So our light source will be a light bulb. This right here is your workstation. The light bulb is going to send rays onto the surface of our workstation. As usual, part of the light will be transmitted, all right, and part will be reflected. We are more concerned about the part that is reflected. But when the light leaves when the light ray leaves its source, it has photons that have spins that are vertical, photons that have spins that are perpendicular. So to draw the perpendicular ones, I'll just make dots going into the board, okay? So these are the perpendicular spins. These are the vertical ones. Every light comes, except it's been polarized, every light ray has vertical and horizontal spins in their photons. If photon A has a horizontal spin, the guy after him will have a vertical spin. That's how they alternate. And the purpose of a Polaroid is to help you separate those photons with a specific orientation in their spin. All right? So what happens is when the light ray hits the surface, it is partially polarized. So first and foremost, recall that we have, when the light ray hits our surface, we have an angle of incidence, an angle of reflection, right? And we have an angle of refraction. I call that R primes, right? So reflection is theta R and refraction is theta R prime. So when the light ray hits the surface, part of it is transmitted through the table because the table will absorb it. Part of it is reflected because your workstation is a dark reflective workstation. So when that happens, the light is partially polarized. What that means is only light of a certain polarization gets absorbed. In this case, let's assume those with vertical spins, photons with vertical spins, are those that mostly go in. So light is just partially polarized. All right? When we conduct an experiment, we will now use a Polaroid right here to make sure that what we see through the Polaroid is light that is fully polarized. You will see how that happens in the experiment per se. So we will spin this Polaroid in such a way that the light ray that we perceive here is light ray of only one particular type of spin. That is now when the observer sees the light, it is completely polarized, okay? It is 100% polarized. And in the course of doing that, we will measure a couple of distances. One of the distances we will measure will be the distance, the horizontal distance from, oh, by the way, before we get there, let me point out something. When this light ray hits the desk, the observer sees what looks like a glare here. So there's a glare here. I like to call it a light puddle, all right? And where that glare sits, as I said, light is being partially polarized because light of certain polarity is refracted or absorbed into the table, and light of a certain polarity, maybe not 100% polarized, is reflected. So when you use your Polaroid to make sure that what you see is fully polarized light in comparison to what was leaving the table, which was just partially polarized, because even though my drawing says, hey, all the vertical spins are going in and all the horizontal spins are going out, in reality, it's a mix. You still have a few vertical spins, photons with the vertical spins here, and a few photons with horizontal spin in here. So the light is still partially polarized. The only way I get to fully polarize the light is with the use of a Polaroid, okay? And in order to do that, I have to find a distance from the glare, the center of the glare, a horizontal distance at which I see the dimmest possible light through my Polaroid. So if this distance is x, when I'm standing right here with my Polaroid, I see the dimmest possible view of this glare right here. And it only happens at x. If I go way past x, I won't get it. If I go closer than x, I won't get it. So this is a standard distance, all right? So I chose this distance. I spin my Polaroid until I get the dimmest view of this glare. This distance has to be fixed. You move it until you feel comfortable, because you have to, at this distance, you should be seeing the glare. Then you spin your Polaroid until the glare is as dim as possible. Once that is done, the next thing you do is you move your Polaroid upward. You take it up a distance y, all right? So let me move my Polaroid and act as though the Polaroid was here. From moving your Polaroid a horizontal distance x, and spinning it to get the dimmest possible view of the glare, you move it a distance y to make that glare even dimmer. So you had a dim view of the glare here, but when you move the Polaroid upward, it got even dimmer. And this too is a specific distance. If you go further than y, it starts to brighten up. If you go lesser than y, it brightens back up. So this is the dimmest possible view you get of your glare at this point. You had reduced the brightness of your glare by moving horizontally, and you've reduced it some more by moving vertically. So at this point in time, what you see is a very, very faint light, which means it is completely polarized. It's light with photons pointing in just one direction, all right? So with that in mind, we know we have a distance y, we have a distance x, we have an angle theta r, theta I, theta r prime, okay? What do we do about that? We now use Snell's law, because we have reflection and we have refraction, and both of them apply to Snell's law. So how do we go about to use Snell's law here? We start with the reflection part of it. I am going to squeeze things around here because we don't have enough room, so you're gonna bear with me, all right? So let me start by raising this surface here, and I will raise the source here so we have some room here. You can still see your angle of incidence, your angle of reflection, and your angle of refraction. So refractive index of medium 1 sine, the angle of incidence should be refractive index of medium 1 sine the angle of reflection. That's Snell's law. All right? And then refractive index of medium 1 sine theta I should be equal to refractive index of medium 2 sine theta r prime, which is the angle of refraction. Those are the two. So this is for reflection right here, and this is for refraction. I hope you can see those two so far. All right. So let's focus on the one about refraction. For the refraction case, that is ni sine theta I equals to n or n1. I'm sorry, I should have said n1 here. Is equal to n2 sine theta r prime. n1 is in air, so this will go away to become 1 times that. All right. So the net result is I have sine of theta I, n2 sine of theta 2. Sine of theta r prime. That is for refraction. I can draw from here the conclusion that the refractive index of my table is given by sine theta I over sine of theta r prime. Remember that theta I is the angle of incident, theta I r prime is the angle of refraction. Next thing I know is that for the case of reflection, so this was for refraction. For the case of reflection, n1 sine of theta I equal to n1 sine of theta r. This is for incident and reflection, but the refractive indices are the same. So this falls out because it's 1 times, the n1s cancel out basically. And sine are just trigonometric functions. So in reality, what this means is, let's keep the n1 here to avoid any confusion. What this means is the n1s cancel out, and all I have is angle of incident equal angle of reflection at reflection. All right. Okay, so these are the two things we know about reflection and refraction. I'm going to have to raise a few things here before we can proceed. We're running out of room, but I want you to keep in mind, if you haven't sketched this drawing, please sketch it so that when I do the calculations, you still follow with me even though the drawing will be gone. So you might need to rewind a little bit, then sketch the whole process before we move on. So do that. I'm just creating room here for further calculations. All right, so we have established our Snell's law for reflection and refraction. What comes next is this. On our drawing, the angle of reflection and the angle of refraction should produce this. Angle of reflection plus angle of refraction should be 90 degrees. Why? Because remember, you had light of a certain polarity go through for refraction, and light of the other polarity being reflected for reflection. And because the polarity is always 90 degrees between the photons with horizontal spin and the photons with vertical spins, the net mathematical meaning of that is the sum of the angle of incident and the angle of refraction should be 90 degrees. Okay? So what that means is this. Mathematically, I don't know if I should go through the trigonometry to explain it all to you guys, but what I can say is, if I apply, I don't have room for this. You can do this at home, basically, right? If you do if you do sine of theta r, right? And try to apply, it is the same as doing cosine of theta r prime, basically. Honestly, if you do that, you will see that that's what it boils down to. If you apply, so if you use trigonometric laws here, you should get this expression, because this in reality just says angle of reflection is 90 degrees minus angle of refraction, right? If you do the sine of theta r here, what you get is a cosine of theta r prime. Likewise, we can also say that the sine of theta r prime is the cosine of theta r. Okay, that's the relationship that exists between reflection and refraction. First, because they have the sum up to give 90 degrees, but secondly, because you can apply trigonometric operations on them. So with that in mind, let's go back to this expression here. Formula 1. Expression number 1 was from refraction that said N2 should be the sine of theta I over the sine of theta r prime. If theta I is equals to theta r, it means sine of theta I is the same as sine of theta r. And sine of theta r is the cosine. So, well, let me do step by step. If theta I, reflection and refraction, angle of incidence equals to angle of reflection. If theta I is equal to theta r, then sine of theta I is equal to sine of theta r. So I rewrite this as sine of theta r over sine of theta r prime. Okay? You guys with me? Now, but I just concluded that sine of theta r is the same as cosine from here. Sine of theta r is the same as the cosine of theta r prime. So I have cosine of theta r prime. This expression becomes cosine of theta r prime over sine of theta r prime. All right? Am I correct on that? I believe I am. But I want to use the angle of reflection. So let me use the angle of reflection instead. Let me transcribe N2 in terms of the angle of reflection. So I'll keep my sine theta I will not change that, right? It will just be sine theta r here. Because angle of incident and reflection are the same. And instead of having angle of refraction here, I will write sine theta r prime becomes cosine of theta r because of this relationship I developed here. So this expression here has been modified using this equivalences here, this identities here. So sine of theta I over sine of theta r prime, which was this expression here, has now become sine of theta r because of reflection over sine of theta r over cosine of theta r because of the relationship between reflection and refraction. This, ladies and gentlemen, sine over cosine is nothing but the tangent of theta r prime. All right? But if you look at your drawing, you had a distance called x and a distance called y. Those two distances were also related by the tangent of the angle of reflection. All right? I'm sorry, this shouldn't have a prime here. Remember, we're doing all with the angle of reflection here. So sine of theta I became sine of theta. Sine of angle of incident became sine of angle of reflection. Sine of angle of refraction became the cosine of the angle of reflection because of this relationship here. And because sine over cosine is tangent, my N2 becomes tangent of angle of reflection. And because on my sketch I had x and y, the tangent of the angle of reflection can also be expressed by using x and y, which was opposite, which is y, right? No, the opposite of that angle, let me see. The opposite is x over the adjacent y. All right? So N2, which is the tangent of the angle of reflection, is the same as the ratio of the horizontal versus the vertical distance. So these two expressions here simply tell me that N2 is I can obtain N2 by doing the ratio of x over y. And that will be the refractive index of your table, of the table surface you use in this lab. What I want you to get out of this lab is two things. For this to be possible, we had to have the Bronsted angle. The Bronsted angle is the angle at which you have angle of reflection plus angle of refraction equal to 90 degrees. It's the angle at which we are able to create these trigonometric identities. You apply the trigonometric function on this expression to create these two. So Bronsted angle is when you successfully have a situation where the angle of reflection plus the angle of refraction gives you 90 degrees. And when you have that, you can apply these trigonometric identities, which you would then substitute into your Snell's law for refraction and use also in your Snell's law for reflection. After doing the substitution of these trigonometric identities, what you end up with is the refractive index of the surface is the tangent of the angle of reflection. But the dimensions that you have for your horizontal and vertical distances to use in creating Bronsted angle can also help you find the tangent of that angle of reflection. So all of a sudden you have two expressions for the tangent of your angle of reflection. You have one that is n2 and you have one that is x over y. What that means is n2 can be obtained by doing x over y. And so we're using Bronsted angle to be able to find the refractive index of your table through the process of polarization. Hope that helps.